So today I wanted to go through the lotka-volterra equations. They're also known as the predator-prey dynamics equations, but it's this and it kind of intuitively makes sense. So we have the change in predator population. If you have more predators, right? So P is predators and H is population of prey. So predators P and prey H. If you have more predators, right, they're going to compete with each other, so it's going to be some sort of negative. And then if you have predators and prey, right, then the predators can eat the prey, right? So that's going to increase the amount of predators, right? And with the prey, you have more prey, right? Breeds more, right? We're assuming that there's an infinite amount of food available to the prey. So like, let's say these are rabbits, right? So we have rabbits as prey. We have foxes as predators, right? The foxes eat the rabbits, but we assume that there's the rabbits have to eat something too, right? They have to eat like grass and carrots, but we're kind of assuming that that they can't overeat grass. So if you have more prey, right, you have a higher birth rate, right, because more of them are breeding. And minus the predators eat the prey, right? The predators eat the prey, so it's going to be a negative in how it changes the population of the prey. And these are just going to be all the constants, the M, the B, the R, the A, and these are the death rate, birth rate for the predator, and death rate, birth rate for the prey. So this equation kind of makes sense intuitively, but we can also do a little bit of checking the units just to make sure it works out. And this is what we're actually doing. So if we take a look at the first equation, we're just kind of rearranging the variables. So we move the HR to this side, and we also divide it by negative A. And we're also rearranging the first equation. So number 1 and number 2, we're rearranging this first equation, and we're actually plugging in h of p, right? So we solved for h of p using the second equation. So we plug in h of p into the first equation. And once we do that, we can actually create, we're basically trying to find how, we want to find like a ratio between the rate of change of predators and the rate of change of prey. And there's like this constant ratio after doing a bit of algebra that you can figure out where the change in predator population, rate of change is going to be the predator's the total population of the predator times the death rate of the predator, and that are plus that death rate of the predator, which is going to be equal to negative birth rate of the predator divided by the death rate of the prey times the rate of change of the prey population minus the total population of prey times the birth rate of the prey. But what we do, what we basically found with this function, like this ratio, is we can actually kind of change the variable. So what I did here is, oh, let me see. Okay, what I did here is basically I reintroduced a new constant, right? Since negative b divided by a is just a constant, I reintroduced a new constant, and I just called it negative c. And that way, I could figure out, I could just basically simplify the problem, right? Since negative b divided by a is a constant, this is also going to be a constant. And for these, m is the birth rate. Sorry, m is the death rate, right? M is the death rate, so I just wrote it as a derivative, right? So the change in death per population, right? So it's the death rate. So if we multiply death rate times population, we get the total amount of death, right? And so I just rewrote everything as basically a differential equation, right? So death rate and birth rate here, right? So the R becomes birth rate, the R here becomes R becomes birth rate, and the M here becomes the death rate right over here. So I just rewrote it as derivatives. And then once I did that, I could take the the derivative with respect to P and with respect to H. So I'm just naming these as total deaths, right? Deaths of predator and total births of the prey. And then I just to make sure, I just wrote C is equal to negative B divided by A as a constant, just to reiterate. So basically, like if we put this into words, right? If we put this into words, we have change in predator population, right? Change in predator population plus deaths in predator, right? Total deaths in predator is going to be equal to the negative births, total births of the predator. And that's going to be divided by change in prey population. There's a change in prey population right here, minus total births of prey. That's going to be equal to total deaths of prey, right? And we know this because of this negative B divided by A, right? So the negative births in predator, that's the B, and then the deaths in prey, that's going to be A, right? And that's how we defined it on the top section. Technically, it's negative births in predator per time, right? So it's going to be make one amendment. This is going to be per time, but the bottom will also be per time, right? Because it's death rate and birth rate. So these two times will just cancel out, as we know from the birth rate and the death rate, right? So once we do that, we'll do a bunch of canceling, but basically what will happen is the negative and the positives, and the negative and the positive, they cancel each other out, and we're left with births in predator divided by deaths in prey, right? Negative births in predator divided by deaths in prey. And we confirmed, right? That's what we get from this constant C, right? That's also exactly the same. And so going through changing the variables, we see that the units of the lotka-volterra equations, they make sense. So that's just a simple way of showing why the lotka-volterra equations why they actually work.